In this video, we're going to look at evaluating limits that have a discontinuity, and we have limits of some rational functions where we have square roots in either the numerator or denominator, and one of the techniques that we might use is rationalizing either the numerator or the denominator. So let's jump into some examples and see what this looks like. Here, if we were to evaluate the limit of x minus 1 over the square root of x minus 1 as x approaches 1, if we tried direct substitution, we plugged 1 in place of our x's, we would get 0 in the numerator. That's not necessarily bad news, but we also get 0 in the denominator. And so that's problematic. This doesn't necessarily factor real nicely for us. There are some things that you could do, but what we might consider is we might consider multiplying by the conjugate. So remember, the conjugate of square root of x minus 1 is square root of x plus 1. All right, so we're going to change the sign right here from a negative to a positive. Similarly, the conjugate of square root of x plus 1 is the square root of x minus 1. So you're just switching the sign between the square root piece and then your other piece. So we're going to multiply both the numerator and the denominator by that conjugate. So we'll multiply the top and the bottom by the square root of x plus 1. Now, why would we do this? The reason why we might do this is it's one strategy that I hope that I desire. I'm hoping that maybe this will lead to some sort of cancellation that will happen. Now, on the top, I'm going to not FOIL it out. It would make things a little bit uglier. But the denominator, I am going to FOIL that out. In that denominator, we'll have square root of x times square root of x, which is just x. Your outer square root of x times 1 is square root of x. Inner negative 1 times square root of x is minus square root of x, so that outer and inner term will cancel. That will happen by design every time when you're multiplying by the conjugate. And then minus the square of the last. So when you FOIL out that denominator, we get x minus 1. And that's really nice because that x minus 1 cancels with the x minus 1 up on top. And once we do that cancellation, now we can do the direct substitution. We can plug in 1. So we have the square root of 1 plus 1, which is simply 2. Great. So that is how we use rationalizing the denominator to evaluate a limit. Let's look at another example. Here we have a limit as x approaches 5 of the square root of x minus 1 minus 2 over x minus 5 as x approaches 5. If we were to plug in 5 directly, we're going to get 0 over 0. That's problematic. So let's see what we can do. Now at the top, I don't recognize how to factor that nicely, so I might consider multiplying both the top and bottom by its conjugate, by the conjugate of the top. So x minus 1 plus 2 is our conjugate. And so the stuff underneath the square root, it stays the same. The thing that you're going to change is outside of that. So that was a minus, it's going to become a plus. So I'm multiplying the denominator by that same thing. Otherwise, I've changed the problem. So when we do one thing to the top, we have to do the same thing to the bottom. The top, then, if we FOIL that, we are going to end up with x minus 1 minus 4 over x minus 5 times the square root of x minus 1 plus 2. X minus 1 minus 4 is simply x minus 5 The x minus 5s, those will cancel. We're left with just a 1 on top. So if we do direct substitution now, we have 1 over the square root of 5 minus 1 plus 2, which will give us just 1/4. And that's the second method or strategy when we're trying to deal with limits at points that are discontinuous, that are not continuous. Right, so in our last video, we looked at simplifying a rational expression by canceling common factors. Here we've looked at rationalizing the numerator or the denominator. Next, we will talk briefly about using the squeeze theorem. You might say, how can I use the squeeze theorem? I don't even know what the squeeze theorem is. That's a great observation. So let's talk about the squeeze theorem. So squeeze theorem says if you have one function f of x and it's bounded below by h of x and it's also bounded above by g of x for all x in some open interval containing c, although maybe not at c itself, then if the limit of the smaller function and the limit of the larger function as x approaches c, if those are approaching the same value, then what that's going to do is it's going to take that middle function, it's going to force that middle function's limit to exist, and it's going to have to equal that same value L. So that is our squeeze theorem. Let's look at a quick picture of what that looks like. So maybe you have some function here, g of x, and as we get closer to c, maybe g of x is approaching L. Oh, that's not how I want to write this. Yeah, let's go with this. So maybe this is our function g of x. And we also have some function h of x. And between g of x and h of x, we have f of x. And the squeeze theorem is called the squeeze theorem because if we know here at c, as our x value is approaching c, if g of x is approaching this value of L, and h of x is also approaching this value of L, if we know that f of x has to live between these two things, since those two things are closing in, squeezing in together as we get closer to c, then that value of L, that function of L, is going to also have to approach, that function f is also going to have to approach this value of L. That is the squeeze theorem. We don't know what's happening over here, but at c itself, f of x is squeezed into that because both g and h are approaching L at that point c. So that is our squeeze theorem. In our next video, we're going to look at some special trig limits, and we will evaluate some limits involving those. We will see you there.